Hey everyone! This video is going to talk about conformational analysis. I'll talk about acyclic molecules, cyclohexane rings, and a new concept called anomeric effects. I want to start by reminding you of what we saw of ethane from Chem 230. We're going to use Newman projections looking down the carbon-carbon bond to describe our conformations. The staggered conformation has the hydrogens on the front carbon and the back carbon 60 degrees from each other. As a reminder, the front carbon is the center of your three intersecting lines, and your back carbon is a circle. Ethane also has an eclipsed conformation, where the hydrogens on the front carbon are directly in front of those hydrogens on the back carbon. In this case, the dihedral angle could be described as 0. And it's known that the staggered conformation is lower in energy. There's actually still some debate the exact reason for why the staggered conformation is lower in energy. Some people would argue sterics, but it has also been argued that hyperconjugation is the main factor. Here is a wedge and dash structure of the staggered conformation of ethane. For hyperconjugation, we want to consider the sigma bond of our CH bond. This is made from overlap of an sp3 hybrid orbital from carbon and hydrogen's s orbital. The hyperconjugation in this case would be a little different from what we've seen in carbocations, in that the sigma bond on the left would be donating into a CH sigma star orbital on the right. In the sigma star, we have an extra node between carbon and hydrogen. Our hyperconjugation would be a sigma bond for a CH bond, donating into the neighboring sigma star CH bond orbital. This could only occur for bonds that are in the same plane, and in this case I'm showing that as my line CH bonds in the plane of the page. Now we'll consider the Newman projections for butane. This will have two methyl groups on a central carbon-carbon bond, and so we'll end up with more conformations because we can have different placements of the methyls in relationship to each other. One example of a staggered structure puts the methyl groups 180 degrees apart. I've shown the skeletal structure above the Newman one here. We would use the term anti-conformation to describe this one, in which the methyl groups are 180 degrees apart. And this is our lowest energy conformation. Another staggered conformation that is somewhat higher in energy is called the gauche conformation. This is higher in energy than the anti-conformation due to steric interactions between the two methyl groups. One type of eclipsed conformation has methyls eclipsing hydrogens. And another way that butane could have an eclipsed conformation is in this case where you have a methyl eclipsing another methyl. This could be called the syn conformer. I've shown in the skeletal structure what this would look like as well. This is going to be our highest energy conformation because we have the most steric clashing between the methyl groups when the dihedral angle is 0. So overall for butane, I have 2 staggered conformations and 2 eclipsed ones. Now let's talk about conformations for cyclohexane rings. Let's consider we just have one substituent, a wedged R group. In one of my cyclohexane chair conformations, the R group is going to be axial, or pointed straight up above the ring. And in my other chair conformation, this R group is still pointed up, but it is now equatorial. A ring flip or chair flip allows me to convert back and forth between these two conformations. Typically, the conformation in which your substituent is in the equatorial position is preferred, because the equatorial sites point out and away from the ring rather than directly up and down from it. We can quantify the preference for a substituent occupying the equatorial position with what's known as an A value. For example, let's consider methyl cyclohexane and the equilibrium between the chair conformations with the methyl group axial versus equatorial. What's observed experimentally is that the equatorial conformation is favored, and the axial methyl conformation is 1.8 kilocalories in mole higher in energy than the equatorial one. Here, E-rel is a relative energy. We would define this 1.8 kilocalories per mole value as being the A value for a methyl group on a cyclohexane ring. The reason that substituents typically favor the equatorial position is due to steric interactions, known as 1,3 diaxial interactions. These are repulsions between substituents at the axial positions. So now, instead of just highlighting the axial R group on my chair conformation, I'm going to draw out the two hydrogens that are also axial, facing up as well. Notice that relative to the carbon with the R group on it, these hydrogens are at the 3 position. These hydrogens are close in space to the R group, and there are steric repulsions between them. You could imagine that the larger the R group becomes, the less stable this conformation would be. And your molecule would have a greater preference for the equatorial conformation in those cases. What's known as the anomeric effect is going to throw a wrench into our predictions for whether groups will be axial or equatorial. So just a couple of definitions to start. The term epimer refers to a compound that differs from another compound at a single stereochemical site. So imagine your molecule has multiple chiral centers. You change just one of these to the opposite stereochemistry, and then your original molecule and the new one are epimers of each other. And for some reason, the term anomers is used as well. This is a term for epimers that became popular in carbohydrate chemistry, and then that somehow carried over into organic chemistry as well. So you may see these words used interchangeably. So, this unexpected conformation, it was first observed in the case of glucopyranose. What was seen is that most of the substituents off of the ring occupy equatorial sites. But at this position, adjacent to the oxygen in the ring, this OH group, about 2/3 of the time it's equatorial, which you would expect based on sterics, but a little over 1/3 of the time it's axial. So this sparked a lot of interest because people wanted to know, why is it ever axial instead of equatorial? So organic chemists got to work and started varying the group at that position, keeping all of the other positions the same. And what they found is that if you change out the OH group for a chlorine, the reaction heavily favors having the chlorine at the axial position instead of the equatorial one. We're going to use frontier molecular orbitals to try to explain why we observe this conformation that we would not expect to be favorable based on sterics. To more generally describe the sets of observations I gave you on the previous page, here we're talking about the fact that there is a thermodynamic preference to put polar substituents next to a heteroatom like oxygen or nitrogen at an axial position of a cyclohexane ring. The type of molecular orbital interaction I'm going to describe is one where, in this case, the oxygen of the ring, its axial lone pair, is going to donate into an antibonding orbital for your carbon X bond, where X could be a halogen, an oxygen, a nitrogen, something like that. But it has to be different in electronegativity from carbon. So here I've tried to show the two different lone pairs of my oxygen. This one pointing straight up is my axial lone pair, and this one pointing out to the side of the ring is an equatorial lone pair. Now I've added my sigma star orbital for my CX bond, specifically with X occupying the axial position. I got this molecular orbital by mixing sp3 hybrid orbitals from carbon and X. And because carbon is less electronegative than the X group, the sigma star has a large lobe on the backside of carbon. When X is axial, this large empty lobe is correctly aligned with the filled lobe of the axial lone pair of oxygen, so oxygen can donate into this antibonding orbital. Just having these orbitals able to interact is favorable energetically and thermodynamically. Now let's consider the other conformation where the X group is equatorial instead of axial. Oxygen and its lone pairs are just fine. Now the other lone pair that was formerly equatorial becomes a down axial lone pair, and the lone pair that was formerly axial becomes up and equatorial. But now that my carbon X bond is equatorial instead of axial, the sigma star antibonding orbital is not aligned correctly to overlap with the axial oxygen lone pair. Now my big lobe is pointing toward the middle of the ring, nowhere near an oxygen lone pair that could donate into it. Therefore, this conformation, even though we would expect it would be more stable based on sterics, it's missing this extra orbital interaction that you can achieve in the other conformation, making it less stable. You'll sometimes see the anomeric effect being referred to as a type of negative hyperconjugation. I want to compare regular hyperconjugation to this new type of negative hyperconjugation. Regular hyperconjugation is typically donation of a sigma bonding orbital into an empty p orbital. We see this most regularly in the case of carbocations, where a neighboring carbon-hydrogen or carbon-carbon bond that's correctly oriented with the empty p orbital of the carbocation can donate some electron density to that carbocation through hyperconjugation. In this particular ethyl cation example I've drawn, a sigma CH bond is donating into the carbocation's empty p orbital. So my orbital donation goes from a filled bonding molecular orbital to an empty orbital. In the case of a p orbital, a non-bonding orbital. Negative hyperconjugation, instead, involves donation of a lone pair of one atom into a neighboring empty sigma star orbital. So rather than having a bonding orbital donating, you have a lone pair donating instead. So more generally, let's consider an oxygen with a lone pair adjacent to our CX bond. In this case, my donor orbital is a lone pair on oxygen. This is in an sp3 hybrid orbital, and I'm drawing this in the plane of the page. In order to have this orbital donate into the sigma star of the carbon X bond, I put the X group 180 degrees away from this oxygen lone pair. This puts the large lobe of my sigma star orbital, that's on the back side of carbon, close in space to the large lobe of oxygen's lone pair. A similarity here is that I have a filled orbital donating into an empty one in a way that stabilizes my molecule. So in summary, in the realm of conformational analysis, I talked about some familiar examples like ethane, butane, and a substituted cyclohexane ring. Then I introduced anomeric effects, which are sometimes also known as negative hyperconjugation, which give us deviations from what we would expect based on what we see in Chem 230. In class, we'll go over some examples where we see these weird orbital interactions that influence conformation. That's it for this video. I will see you in class.